Assalamualaikum. Today's episode is a revised excerpt of a past upload on the rate of thermal conduction. What are the factors that affect the rate of thermal conduction and how do we compute the thermal conductivity of a given metal? Please stick around till the end of this video. Watch and learn. Conduction is a mode of thermal energy transfer involving collisions of atoms or molecules. As illustrated in the drawing, a conducting metal rod with a given length and cross-sectional area is seated at one end labeled A. The opposite end labeled B is cooled by immersing it in an ice-water mixture. We can determine the rate of thermal conduction by measuring the amount of ice that melts in a given length of time. This energy is transferred from the left end to the cold end or from the hot end to the cold end of the rod. The rate of conduction is determined using the equation capital Q divided by T is equal to quantity K times capital A times delta T divided by L, where big Q over T is the rate of thermal conduction. Of course, big Q refers to the amount of heat that is being transferred, and small t is the time during which the thermal conduction is happening. Capital A is the cross-sectional area of the rod. Capital L is the length of the rod. Delta T is the change in temperature, that is, capital T sub B minus capital T sub A. And small letter k is the constant known as the thermal conductivity constant of the conducting material. And based on this equation for the rate of thermal conduction, we can see that the quantity K, the cross-sectional area, and the change in temperature, each of them is directly proportional to the rate of thermal conduction. And the length L is the only quantity that is inversely proportional to the rate of thermal conduction. The question is, one end of an insulated metal rod is maintained at 100 degrees Celsius, and the other end is maintained at 0 degrees Celsius by an ice-water mixture. The rod is 60.0 centimeters long and has a cross-sectional area of 1.25 centimeters squared. The thermal energy conducted by the rod melts 8.50 grams of ice in 10.0 minutes. The question is, find the thermal conductivity denoted by letter K of the metal. We're given the following information. One end of the metal rod is maintained at a temperature T sub 1 equal to 100 degrees Celsius. And the other end of the rod is immersed in an ice water mixture. okay, at a temperature of 0 degrees Celsius. 8.50 grams of ice is melted in a period of 10.0 minutes. The metal rod is 60.0 centimeters. That is the length of the rod. And it also has a cross-sectional area equal to 1.25 centimeter squared. And we also need the constant latent heat of fusion of ice, all right, for our computation. This is denoted by capital S of F equal to 33.5 times 10 to the fourth power joules per kilogram. Moving on to our computations, we first find big Q, or the amount of heat that is required to melt the ice. So, big Q is just equal to the product of the mass of the substance and the constant latent heat of fusion. That is, big Q is equal to 8.50 times 10 to the negative 3 kilogram multiplied by 33.5 times 10 to the fourth power joules per kilogram. So, multiplying these two quantities, we get the value of the heat that is required to melt the ice, or big Q, equals 2,850 joules. We can now proceed in computing the thermal conductivity of the metal rod, denoted by the letter K, using the formula. K is equal to the product of big Q and its length L divided by the product of the cross-sectional area, capital A, the change in temperature delta T, and the period of time T. So, when we substitute, all right, the thermal conductivity constant K is just equal to 2,850 joules multiplied by 0.600 meters. All right, so all over 1.85 times 10 to the negative 4 meter squared. And that is multiplied by 100 Celsius degree and 600 point seconds. All right, this is the time it takes for the given amount of ice to melt, right? This is actually 10 minutes, and that's equivalent, of course, to 600 point seconds. So when you do our math, we get the value of K equal to 228 joules per second meter Celsius degree. And this computed value of the thermal conductivity of this metal is pretty close to the standard thermal conductivity of the aluminum metal. So that ends our lesson for this topic. Till the next episode, mabuhay. Mashallah. Thank you very much for your indulgence. Please don't forget to subscribe to my YouTube channel. Alhamdulillah.